Hello, world. I'm Farsight, and this is Kerbal Space Program 1 with the RP1 mod loaded. I've added to it Kerbal Operating System, KOS, and we are going to be using KOS to control our spacecraft in RP1. The career at this point has advanced to where we have picked our programs and our contracts, and we are ready to start building our first rocket. I'm going to do a load so we can pick up this particular save, which is a stable point where I want to start. It's a save I just made. But yeah, I will start the episodes by loading up a save game. So things should be repeatable in case I have to rebuild a save game. So to build our first rocket, this is going to be a sounding rocket based on the WAC-Corporal, which has a small solid fuel booster strapped to it. And I can turn things on and off, and I'm mostly going to turn it off because to my eye, this isn't a lot of real estate. I'm used to working on 4K instead of 1080p, so yeah, give me a little bit of a break. It seems a lot smaller. So the first thing we want, we need to have avionics. You start building your rockets in KOS from control down, so it's top down. So at the tip top of the rocket, we have a control thing, avionics, which is going to be a cone. We're not going to be actually configuring it yet. We're going to start configuring it once we've got some of the parts laid out. Now's the time to actually save it. I don't use fancy, I could call this a WAC-Corporal, for instance. But the problem is you end up with a whole bunch of rockets with various names, and when you look at the list of rockets, they're in alphabetical order. What I want to see is I want to see the rockets categorized, so I have all of my sounding rockets together and all my downrange rockets together and so on. And then within that, I want them to start out with the simpler ones and go to the more complex ones. So this is sounding rocket configuration 1. And it's going to be sub-configuration A. The idea is that we're going to end up with sounding rockets that get bigger and smaller, and maybe we'll go back to an earlier rocket and put a better engine on it. So here is our S1A. Well, no, just call this S1. The question is, am I going to have more than 10 configurations of a sounding rocket? And maybe not. So let's do this. I will deal with the fact that rocket 11 is going to be between rocket 1 and 2. I can deal with that. If I have to, I can go back and I can rename the rockets. The S1. Sounding rocket to reach 100 kilometers. And save. So as I build rockets, I will be picking up some starting point and immediately saving it under the new name, so I never will destroy the old rocket if I make big changes for the new one. So there's our avionics. We will configure that later. We are also going to need some fuel tanks, and we're going to be using procedural tanks. Procedural just means that we can select the diameter and the length and the shape and all of that. We could build things out of modular tanks, but these are so much more configurable. Also, the tutorial does it this way. I'm trying to stay close to the tutorial so you all can follow along, and it makes it that much easier because my main focus really is on I want to write KOS code. So if it were just me, I would kind of zoom through all of this stuff and get up to the fun stuff. Where for me, fun is writing code. So scrolling forward, we need the nose cone, which has the avionics, we need the fuel tank, and we need an engine. And that engine is the Aerobee, which is a small pressure-fed engine, as it says there. This engine has some properties that are interesting. For example, if there's a bubble in the fuel tank, and there will be when you start burning fuel, there will be a bubble in the fuel tank. The end of the fuel tank near the arrow B can't have the bubble in it, or the engine will stop. So you have to have you either ignite this on the ground, or you ignite it in the air, but something else is pushing the rocket forward, so you get some acceleration. So the fuel comes in. It's called ullage. If you're flying along and your nose drops below the horizon, the engine will probably flame out, because that bubble will probably hit there, because you probably don't have enough acceleration to make the bubble think it should be in front. Anyway, so this is a engine that you start under acceleration or on the ground, and it keeps working as long as you're going up, and that's great. So, engine. We have a number of things we can configure, and there's a big GUI. We cannot do it yet, but eventually we will be able to upgrade these engines in place to XASR 1s and AJ 10s. This is a ways in the future. The interesting thing we want to look at here is we want to double check that our thrust is appropriate for the vessel we're building, and we know it is because we are building basically we're reproducing in-game a real-life rocket called a WAC-Corporal. So we know that this is going to be appropriate for the WAC-Corporal. We can see down here I've got MechJeb's Delta V stats going, and we've got no fuel, so it's not going to show anything yet. It shows what kind of fuel we have, and the interesting thing we want to watch here is the rated burn time. This means that this engine can fire for 47 seconds, and after that, its chance of failure goes up very rapidly. What I didn't know until I went through the tutorial is the first 5 seconds of the burn time of the engine is highly unreliable, and the rated burn time starts after that. So we want to tune this engine to actually burn for 52 seconds, a bit over 52 seconds. Put that in your head, 52 seconds. Now there is a flight test window, which you middle click on the part, and that shows you a whole bunch of flight data. So for instance, there's a flight data quantity there, and as you accumulate flight data, you get more reliable. So currently, this engine's about 1 chance in 6 of failure, and we should see them fail about once every 5.5 minutes. And once we have collected 10,000 units of flight data, then their failure chance is much lower. So 93% reliability at full burn, and about 11 seconds mean time between failures, or 11 minutes. So using these over and over makes them more reliable. This also means that the first few launches we have a pretty good chance of not working right. Currently, 9 times out of 10 it'll ignite, and that maximizes out to 96%. Cascade failures is if you put a bunch of them together and one of them fails, it may cause the other ones to fail. There's also failure chance as the pressure goes up. We have disabled that, so we should not see this getting failure to ignite due to pressure. And there is no restart on this engine. You start it once. If it flames out, you can't start it again. It can only really be restarted on the ground. So, configure the tank. Toss the engine over here in case we need to refer to it. The other thing to know from the engine is its diameter is 300 millimeters, or 3,000 millimeter. That will be important right now, where we are building the tank. So the Aerobee needs a high pressure tank. We can see here, propellant needs high pressure tanks. So tank type needs to be HP. The easy way to do that is to hit the choose tank type button. And of course it pops it up on top of the Aerobee window, because of course it does. Maybe I can put the Aerobee window over here, tank window over here. these colored pop-ups that come up tend to be over in this area. So we only want unlocked, and we want highly pressurized. So our choice here is HP steel fuselage. So we have now selected our tank type. And it knows what kind of engine is attached to it, so we can say fill it with fuel. And now MechJeb is reporting that we actually have fuel and we can burn this. And this would burn for 143 seconds. Well, we need to have that be slightly over 52 seconds. So now is the time for us to change the size of the fuel tank. That's up here. I'm going to close real fuels now. And let's see, shape is cylinder, that's correct. Diameter needs to be 300 millimeters. Notice how that just fits very nicely with the engine there. And now we can modify the length until our burn time down here is our 52 seconds that we want. So between 3 and 3.1 meters. The tutorial, we want to match the tutorial. The tutorial picked 3.1 meters because remember we want to go slightly over. Having a little bit of extra fuel is good because the engine might last longer than its rated length. And if it does, then you've got the fuel to make it available, so go for it. If you extend it too much, then you'll be carrying a lot of fuel that you almost never use, which is just extra weight, which just means you get less acceleration. So it's a careful decision as to how much excess burn time. Okay, that makes that easy. We were able to configure it fairly quickly. Let's get rid of those. And now we can configure the avionics. So I have conflicting information on the Aero B. On the one hand, the tutorial says use a smooth cone. It's got this nice curved shape. It has a blunt, slightly blunt tip. And then I look at pictures of the WAC-Corporal in the museum, and the cone looks like literally a cone with a sharp, pointy bit at the front and a sharp angle where the cone fits into the cylinder. So you could go either way. I am going to go with a smooth cone, like it does in the tutorial. We're going to go to type in the numbers here. So the top is 0. Generally, zeros are not all that great. You want to make sure when you're putting in a 0 that it's not going to result in a surface of 0 width. We want 0.30, oops, not for length. 0.300 is the diameter of the bottom. So you notice how that suddenly just kind of flows into the fuel tank. I could color them differently to make it obvious where the line is. I will be painting these later. Length. It needs to be long enough that our cone has enough space for the avionics we want. And they're using 1.5 meters. I think it sounds like they're making that decision based on aesthetics. So in the real world, the longer the nose, the more aerodynamic it is. I don't know whether that is true in KSP1 or not. But let's go with something that looks right, and that looks right. There's our rocket. That actually doesn't look bad. I could just use the little silver rockets. I don't need to actually color it. So configuring, almost forgot, you do need to configure, I was starting to think about the fins at the bottom. We do need to configure the avionics now. This window is the one that Remember we turned off one of the windows that automatically always comes on? That's this one. So we have avionics. We have two types of avionics we can have. One is full control of the craft. So if we had like steerable rockets or steerable vanes on it, we would use this. Uses LV ascent guidance and upper stages that operate around the Earth. Okay, so Science Corps is a much simpler avionics. It just provides, provides a place to put your science instruments, but it doesn't actually do anything. This is for unguided rockets, and this is an unguided rocket. Tech level, we are going to use the starting technology. We cannot upgrade to any of these yet. Our first upgrade will come when we finish post-war avionics, and that adds a bunch of things. Mainly, it makes it lighter and take less, stuff. So this has 40 kilogram mass, 100 watt power consumption, no control. This, less mass, so from 48 kilograms down to 33, power is down to 50. So the upgrade from post-war avionics means less mass on our nose cone, so more mass available for payload, or maybe you can go higher and faster. So down at the bottom, we need to put in some electricity. They suggest 100 kilojoules. They're going to apply and preserve the dimensions. There is a place where it shows how long the electricity lasts. There we go. Look in the avionics selection of the PW. This is the PAW here, this window. So under avionics, this now has information that we are using 24.1% of the space. It needs 100 watts. There's its mass, cost, and it's a science course. So we have most of the information from here that we're interested in back in this window. So they suggest the default antenna for these has a 30 dBm gain, and they say you only need 20, and that's not something I have played enough RP1 to just know. I'm just going to follow along with the tutorial on there. You can go with a 20 dBm antenna instead of a 30, and it apparently gets lighter. If we get to flights where we cannot do our work because our antenna isn't good enough, then we can boost that. Science experiments. Figure experiments here. So we have two experiments we could do. We have a thermometer, and we have a barometer. And here we want to set these to waiting so that when we get to a biome where we can get a temperature reading or a pressure reading that is meaningful, then it will do so. So under RP1, your science instruments automatically collect their science. You don't have to rush around and clicky, 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 clicky on them. There is a sample capacity, and we do not need a sample capacity, so we are just going to leave this at 1. That's fine. And that's our avionics sorted. The next step is we need to put some fins at the bottom. I'll show you why. Here is our center of mass. And here is our center of aerodynamic. And yeah, not right. Center of lift needs to be on the other side, doesn't it? It does, yes. Center of lift needs to be behind the center of mass, where you tend to do things like flip your rocket upside down. So to fix this, we are going to add some wings on the bottom. And the WAC-Corporal that we are trying to match has 3 wings. we're going to scroll down and we're going to pick up the B9 procedural wing early. So procedural just means that we can set its size. Delta Deluxe is the one that I used to use a whole lot in normal KSP, and it's a lot bigger than this. So we grab the procedural wing and we're going to put 3 of them on. We can adjust its position later because it's just huge. B9 procedural wing. The only thing we're interested in tuning here is this mass strength multiplier. You can reduce the mass of your wings by changing the strength of the materials. So you reduce the strength of materials and their mass. And we will be tuning that. You reduce that, it's lighter, it goes farther, it goes faster. But that means that under certain aerodynamic situations, the lighter one might break off where the heavier one might survive. So to set the geometry of these wings, it's not in here. You mouse over this guy and hit J. And there you go. We've got all sorts of drag handles. We can move things around. Let's turn off, let's turn off our overlays for the moment. And we can change the length. We can change the width at the root. We can change the width at the tip. And then thickness and so on. And we've got configurations for the leading edge and trailing edge. So by default, we have a rounded leading edge and a biconvex trailing edge. So the biconvex just means that shape there. So for the tutorial, I'm just going to put in the numbers. So 500 millimeters long. The width at the root is 50 millimeters. Width of the tip is 050. So the base of this thing is a long, thin strip. And then we're going to have a long leading edge and a long trailing edge. So that gets us kind of an airfoil shape. Thickness at the root is 0.025, so 25 millimeters is the thickness of the wing. Now see how that works with the panel itself, and then you've got a leading edge and a trailing edge. And to select this, you have to mouse over this center part. Leading edge and trailing edge do not get a select, so this is a good reason to paint this part. Now we want to make it look more like an actual wing. So take the leading edge and we make it 200 millimeter length at the root and only 50 millimeters at the tip. And the trailing edge we're going to make 300 millimeters at the root and 100 millimeters at the tip. That's looking a little more useful. Next thing we want to do is offset the tip vertically so that this is horizontal. And that's just here, 200 millimeters down. And there's our winglet. And now we want to put it in the proper place, so I'm going to grab it. Now I like to use the horizon for finding horizontal lines because if you are looking straight out at the horizon, you are looking level. Specifically, if you're looking at a spot on the horizon at the same altitude as you, it's exactly level. But plus or minus a little bit, it's a long way away, so that angle stays pretty much level. But now we can take this, and I can make it pointing directly toward me, move it up and down until this is exactly where I want it. Just like that. We can do it this way, or you can move it all the way down so that the rocket fins are down below. I can move this down. And remember that thin strip at the middle? As long as that thin strip is on the fuel tank, we're good. But we go below it, Yeah, that's right. Make a liar out of me. This connects it to the engine. That's cool. I'm just going to put it here. I didn't know you could connect it to the engine, and we're going to do that. Now, we could get fancy. We could put a cowling over the engine, but I'm just going to leave the engine exposed. Those look pretty good. So the next question is, how does this affect our aerodynamics? So here's our center of lift. So center of lift is way behind center of mass. So if we were flying off at an angle, our center of mass by inertia would go in that direction. The center of lift would be pushed back behind it. If we were in front of it, it would be pushed out. So that's proper. What happens as we empty out the tank? Well, we have a little helper for that. The RCS build aid can be configured to say where will our center of mass be when these things are empty, and you light the spot up to say leave these full. So when we have emptied out all these resources, our center of mass will have moved forward a little bit. So we want the center of mass to always be a healthy distance in front of the center of lift. And nobody ever defines healthy. They all say, oh, that comes with experience. So what you do to get experience is you fly the rocket with a center of mass really close to your center of aerodynamic pressure, and you see what happens. You move it around and you find out where things break, and then you make it separate a little bit more. Or what we do here is we look at it and say, looks good. Although in the tutorial they say 0.5 meter length fins seem a little large, so lower them to 0.4. We'll do that. Again, I have to mouse over it to find that strip there, because I haven't painted it yet. And they're suggesting reducing the length to 0.4 meters. You notice when we did that, our aerodynamic center went up. And apparently this is still a healthy distance. That's fine. By reducing the length, however, I think we also reduced the mass slightly, which meant slightly more delta V, which is always a good thing. The other thing is he wants to reduce mass strength multiplier to 20%. Again, notice our center of mass moved up. What you really want to do if you want to fine-tune this is you keep test flying it with smaller and smaller mass strength multipliers, and when you break it, you increase it a little bit, and you keep increasing it just a little bit until they don't break off when you do normal things. So one of those normal things is if we launch this rocket at a 45-degree angle, we get some aerodynamic stresses at the moment when the booster is released, and do those transient aerodynamic stresses knock the thing off. We're just going to use 0.2 here because that's what is in the tutorial. Okay, so far so good. But the WAC-Corporal also has a solid rocket booster. We go back to engines. We pick up the Tiny Tim. We're going to use one of those. We do need a separator. Go to coupling, and we pick up the hollow interstage. Well, the reason why we want this as hollow is because we are going to have to light the aero bee before we jettison the booster. If we jettison the booster, the rocket will be basically, free fall plus drag, which means all the fuel is going to be pushed to the front of the tank. We need it at the back of the tank. The aero bee won't light, so we need to light the aero bee with the rocket present, which means hollow interstage so that all the fire coming out of the aero bee has someplace to go. Let's configure it. First of all, the core, it's actually a configuration here for the aero bee. This is actually how it looks on the aero bee. It's this little spike here that takes all the thrust coming out of the aero bee and diverts it out the side. Second thing is the diameter, which needs to be the matching diameter for the rocket. And that looks really good. Now, we left our center of mass and aerodynamic center here. So you can see that at the moment we launch, our aerodynamic center is slightly in front of our center of mass, and as we burn our solid fuel, center of mass, oh, adjustment. RCS build aid, we're going to say, show me what happens as we burn just the NGNC. So we're going to say, show center of mass with full, these three guys full and NGNC empty. So this shows us that our center of mass starts slightly behind center of lift and moves forward. So we might get away with it. Might being operative. However, that's not a healthy distance. So I am going to copy the fins down. So I hold down Alt and left click, and that gets me a copy of the fins. And we're going to put them all the way down at the bottom. Just like that. And we now see that our center of lift is, it's a ways below. And the tutorial now moves on to the launch clamp. Apparently this is still healthy. So we can turn this off. We're no longer worried about our build aid here. We can turn that off. Now we need a launch clamp. Modular launch pads has launch clamps. We want a small one. Sort by size. We're going to get a whole bunch of things that are... These are launch clamps? Oh, modular launch pads include a whole bunch of modules for the launch pads. They also include the milk stools. We want just a launch clamp, and I guess that's up in structural. Yeah, here we go. We're looking for the small launch clamp. There we go. And that will hold the rocket in place. Now, we kind of place these all arbitrary. If I hit B, B will pretty much center this stuff up. And I think if I move this guy way over there, yeah. So hit B, and it will drag everything in so that it's at appropriate distance above the pad and centered, or some value of appropriate and some value of centered. So all of our parts are there. Now's the time to check your staging. Notice down here, the staging that it defaulted to was we are going to ignite the engine, and then shortly after that we will release the launch clamp. At the same time, we're also going to release that, and then we're going to start the aerobee. Well, that is all wrong. First of all, let's separate these out. What I want to do is ignite my booster, and then I'm going to release the launch clamp when the booster has developed enough thrust to get us off the launch pad. Now, for this guy, it's immediate, but I want to use this logic in general. This way, if the engine doesn't start, we never release the launch clamp, and everything is still there on the launch pad. We can roll it back in and we figure out what's wrong with it. If it ignites and doesn't produce enough thrust, we hold it in place, because if we release the launch clamp, we don't have enough thrust to get it into the sky. We just kind of fall over and things destroy themselves. So keep the launch clamp until we have more thrust than weight. Once we have more thrust than weight, we're going to release the launch clamp, and then we're going to fly up. And when the thrust from the solid rocket booster gets to zero, or gets too low, when the thrust gets so low that it's doing more harm than good, we want to detach. But before that, we want to light the aerobee. So when the thrust gets down below some threshold, we're going to ignite the aerobee. And then when the total thrust balances out to where the aerobee is running, we're going to ditch the booster, because the threshold we're going to choose is such that the booster will no longer be producing an interesting amount of thrust at that point. So our software will have 4 staging commands. So ignite, lift off, ignite the second stage, and separate the first stage. The only other thing that we are going to be doing in our software, if we even do it, is to log some data about the flight, maybe print some things, maybe draw some things on the HUD. The initial version of the code will not do any of that. I'm assuming I will get all the information I need from MechJet. Painting this mother. The first critical thing is I want to have a different color for the stripe on the middle of the wings. This is a real thing. So here's the procedural wings, and we can recolor it. And let's see, the tutorial colors it for clarity of the tutorial, but I'm going to put a white stripe down the middle. So surface main is going to be white paint right down the middle there. Section is this little bit out here. It's on the edge, on the end here, and we're going to make that white as well. Now, that looks wrong to my eye. I want to sneak this up a little bit so that joins with the main guy. We'll see where we're going to put it once we've got the paint job done on the top. Yeah, I don't like that white stripe going into the engine bell. So, leading and trailing edges. Let's make those metallic black. And these parts don't have any fancy texturing on them, so there's no secondary detail on it. I'll do the same thing down below here. So if I had painted these before I copied them, it would have just inherited it. Oh, come on, close. Close you. Right click on there because it's in this window, not the other one. So surface main is white paint. Section is white paint. Leading and trailing edges are black metallic. Black metallic gets that really nice, deep, shiny black that I like to see. So, Tiny Tim. Tiny Tim can't be painted unless you switch to the TU Recolor variant, and then you can repaint it. Open Recoloring GUI. What we have here is a base color and some stripes. I don't think we get to pick a different texture. I am going to take this stock variant, the recolor here. This lighter area is going to be white. And the darker area I'm going to make shiny black. Now we could flip these. Yeah, black stripes on the white parts is actually more interesting now that I think about it. Close. Let's swap our colors here. So the surface main is going to be black paint and black. Leading and trailing edges, those will be white paint. So let's see, white paint and white paint and black and black. So basically we're going to do a white rocket with black parts, black things showing up. That's cool. We can do that. Close. Now the tank, we have plain metal. We can change the way that's patterned. Stripes are good. Now the arrow beam, I think I'm going to go with this layout. So the sides, recolor, we're going to go with light parts are going to be white. And the dark parts are going to be black. ends are they top and bottom? I don't think those really matter. Now we want to paint the nose cone in a way that kind of works with this. Oh, almost forgot. We'll do KOS last. Nose cone. We have all of these choices for coloring schemes. Kind of like that one, but with this middle part white. And we're going to open the recoloring tool, and the light parts get lighter. And let's see, quick paint, and the dark parts go full on dark. So there is our S1 sounding rocket. So in the tutorial, they use MechJeb to do their flying, and they give a really good justification for not flying by hand, which is NASA never did it, why should we? They also have a comment about this is not Kerbal spacebar program, so we shouldn't be hitting the spacebar like boom, 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 to try to get the timing right by our hands. Automate it. They automate it with MechJeb. I'm going to automate it with KOS. But let's close down all of these little arrows. If I remember to close them, it means they should tend to be open, or they should tend to be closed when I open it again. And that's good, because that keeps the window small, because we're only on a 1080p screen. Open out KOS, and I'm going to say, when I switch to the vessel, KOS boots its internal processor, and it's going to start running this script called boot.ks, which is part of Farkos. Boot.ks does some things for us, which it's going to do for every vessel, and it loads up a standard little library which gives us some support code that I want on every vessel. Then it turns control over to our avionics code, which for S01, let me just bring it up here. There we go. So, what do we have here for our avionics? If you haven't looked at my Farkos stuff from a year ago, this is easy enough. Just ignore everything and say, there's some boilerplate here, and where we say go add go, this is saying our package is called go, and we have a method in it called go. This is like public static void main whatever, or just void, just int main argc and c. This is where we start executing. We have, before we get to here, we've done some vessel independent startup, which can run for any vessel, and in fact for long running vessels it can run every time we switch to the vessel. And what are we doing here? Well, I need to pre-compute the weight of the ship, and I added some comments there because first thing I thought was, if I have this line here saying weight is ship mass times body mu over body radius squared, people are going to say, oh, wait a minute, doesn't your weight change as you burn fuel? Doesn't your weight go down as your altitude goes up? Doesn't your weight change significantly when you detach the booster? So this is my nominal vessel full weight, including all fuel at 100% capacity at sea level initially. And this is going to be a specific amount of force that I want to use in my logic. So this code does 5 things. It ignites the booster. Well, here is our first stage. It's going to be igniting the booster. Ignite the booster after a short delay. We're going to release the launch clamp, so we're going to wait until our thrust is bigger than our weight. And we're going to release the launch clamp here in stage 2. Then we're going to wait until the thrust drops below half of our weight, so the booster is going to be pushing us really hard, And these don't cut off to 0 immediately, they ramp down. So when we've ramped down to where we're only producing half of our weight in thrust, it's time to light the arrow B. The arrow B is going to ramp up, and when our total thrust is again above our weight, so the arrow B is kicked in, and between the arrow B and the booster we're back up to snuff, we're going to jettison the booster. And I have not actually tested this logic yet. We're going to test it for the first time in simulation. And I think what I'm going to do to keep a little bit of suspense going, I'm not going to record simulations because they happen in virtual time. When we go into simulation, I will pause my recording, and you will see flights as they happen committed to the actual career. So you see a flight that is something that I'm committing to, I'm spending real career resources on. So what are the steps we have to do? What does the code look like? Ignite booster after short delay. Give me 5 seconds to open up the KOS window and interrupt it if I want to do something other than fly today. And then we stage. Always wait until stage ready before staging, because otherwise you might have multiple stage commands that don't happen. Release clamp when thrust is enough to lift off, so we wait until ship thrust is greater than weight, and we wait for stage ready and stage. I can combine those. So wait until we have enough thrust and we are ready to stage, then we stage. Then we wait until the ship thrust is low, then we stage. Now we wait until thrust is back up above weight again. You're probably seeing a pattern here. Wait until condition, then do thing. And then at the bottom, we're saying wait until false. If I fall off the bottom, okay, then it's going to release all the controls. Now, if we had a throttleable engine and we fell off the bottom, then the throttle would go to whatever the user input is. If we had a way to steer the vessel, fall off the bottom, and the vessel steering then gets released by KOS and it goes to whatever the inputs are from the user. So even though for this rocket, once we've jettisoned the booster, well, we could wait until we have no thrust and then stop. I am just going to keep KOS spinning here. If we do this way, this means that potentially I could add code in the future up here at the top that says, when this happens, do this. Literally, when some condition, then, and a piece of code that will execute asynchronously in the background when that condition is true. Called a when then. It's a triggered thing that happens in the future. Your code keeps on running. Just when that it evaluates that condition every physics tick. And if the condition ever comes up true, it's going to interrupt your code and go do that other thing and then come back. You don't want to put a lot of those, but they're useful. For example, auto stagers can be written that use this, so you don't care whether you're auto staging in the middle of a maneuver or not. Middle of maneuver, you're just going to suddenly auto stage, and yeah, most maneuvers are going to be really messed up by that. But if you're doing something dynamic like circularizing your orbit, which doesn't require a maneuver node, by the way, you can circularize with math. Middle of that, you suddenly have to discard one stage and go on to your final stage. You just stop burning, you change stages, you can go back and you start circularizing again. And the circularization code doesn't have to know the staging might happen. It just keeps calculating what it wants to do and doing it. So there's the code. I like leaving things folded like this because having them open invites you to look further into details that you don't really need to see when you're looking at an overview. The other way to do this is for each one of these steps to be a subroutine. We look at the subroutines that would come down here. For really simple code like this, it's a matter of taste for me. I can go back and forth. This code, I like it inline like this. As you get further into Farkos, you'll see that there's a whole mission sequencer thing that allows you to like go back earlier in the sequence and store where you are in the sequence in all volatile memories, so that when you come back to the craft later, you can pick up at the same place in the sequence. That'll be really important when we have missions that go for a very long time. Interplanetary missions, I'm looking at you. Well, there's our code. Let us turn it off. And that is our design of S1. We do have contracts, and we can't build it quite yet. But what I'm going to do now is I'm going to chop this video, and I'm going to start a new recording, and I'm not sure how this is going to lay out in terms of episodes on YouTube. I tend to start every recording with my normal intro, just in case that's the start of an episode. But we will come back with doing all of the RP1 stuff that it takes to get this built. I will simulate this a number of times offline, and at the beginning of the next recording, I will discuss anything that I had to fix during simulation. Then we'll go build the launch complex. We'll go tool the rocket up. We will hire people to do things. We will build the rocket, and we will launch it. And I will see you in that recording. So between now and then, go have some fun.